Okay, good. You're welcome back. So, so today I will be like discussing on this advanced computer vision technique for bridge health monitoring. So I think I think by now you guys would have understood what is like computer vision. I mean like more advanced topics you have covered, but I just want to like give a quick recap of like some basic structure health monitoring. Then we'll touch upon some of the works that we have carried out. Okay, so I will show some of the work that has been carried out in Japan as well with some bridge experiments we have done. Then also like we'll show some like small experiments which we plan to do on the bridge. I hope by now you would have understood which bridge I am mentioning. Okay, so we have done some work, so that also I will try to show it at the end. So it will be like rather than like a lecture, it will be like a small presentation, and it will open for the discussion. Okay, so we'll exchange ideas. So that's the main purpose of this session. So 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 this is the London Millennium Bridge. How many of you are aware of this bridge? What is the speciality of this bridge? Someone? Of course, this is in London. So what is the speciality of this bridge? No. Okay, let me just play this video. I hope it will play. So what you can understand from this video? This video has been taken by some tourist visitor, okay, and where I think it has stopped. And this is called as something like wibbly wobbly bridge. So what you can observe from this video? Some observation as a civil engineer or as a structural engineer or like a dynamics or a health monitoring expert, what you can observe? Yes, very good. So you can feel the vibration. Okay, so this was something like constructed in around 2000. Okay, then it was immediately stopped for the traffic because whenever the pedestrian was using it, they could able to feel the vibration. They were so much afraid. Then there was an expert committee, so which has formed, and there are a lot of dampers which has been kept. I hope you know what is the usage of dampers. Okay, it is going to control the vibration. Okay, that has been installed, and again it has been opened in 2002. It has been opened for the pedestrians, and till date you can feel the vibration while you're walking. I had an experience in around 2016, so we were having some experiment here. So this is something like funnily called as wibbly wobbly bridge. Even this was in YouTube. You can just open source, you can Google it and you will understand. So now the point is it safe or unsafe? As a civil engineer, please answer it. Is it good, bad? What do you think? Bad. It is unsafe, uncomfortable, but like people enjoy it. People come to Big Ben, after that they come to this bridge and they cross it, they jump it, they run, all those things happen. And why this oscillation is happening? So why you are feeling that vibration? So for example, like when the pedestrian is walking, okay, so let us assume that there is a random crowd walking over this bridge. So I hope you would have seen these minions. Have you heard that like you try to like disturb the minions, set of minions at different time, at a time of fraction of minutes or like seconds, it will synchronize among itself and it will be having a same frequency. Similar thing is happening here. When pedestrians are randomly walking here and there, at a point of time, the oscillation, the lateral oscillation is somewhat having a synchronization with the pedestrian walking, and the bridge is having that vibration. When it is going to match with the natural frequency of that bridge, what happens? Resonance happens. So which is very unsafe for us, right? So more or less it is happening. That's what is happening, which has been like controlled using a lot of damper system. Okay. So these are all some of the mode frequency which has been taken from the study that has been done by the Italian professor in around 2000. Okay, so we'll be using this. Why am I showing this at the beginning? Because like something, these are some of the case studies which till date we are using. Okay, so it is like very good to understand the dynamics behind the bridges and why health monitoring is more important, particularly for the bridge infrastructure. Okay, that's the reason I would like to show this first. Fine. So Shinkansen, I hope you would have heard about this word. What do you mean by Shinkansen? Bullet trains. Okay, so Shinkansen is a Japanese name. Okay, so this is something like a picture that has been taken in Japan. Okay, so it's like an old reinforced concrete viaduct. Okay, so I hope you could able to observe viaduct 6 and 7. So it is something like an identical design. Okay, so it is in service for 40 years. Okay, which is like good number. So now the point is they want to increase the speed from 210 km per hour to 270 km per hour, which is hypothetical condition in India, but in Japan it is possible. So the question is that I think it's in red color. I hope you could able to read it. Responses of these identical viaducts are the same under train passage. Yes or no? What do you think? So imagine a train is going to pass in 210 km per hour, and this is something viaduct 6 and 7, which is very close. It will be like in 1 second it will cross the viaduct. So how the response will be? Suppose if you are going to install an accelerometer, okay, and you are going to collect the response. The question is whether the response is same or not. Yes or no? Viaduct is something like a structure. It's like a, no, you can see the structure, right? So where viaduct is something like underpass, like you could able to use it. It's like a bridge structure. It's like an RC structure where railway system, railways is passing. Yeah, it's like an identical viaduct. It's like a separate structures. It has been divided into two. There are like number of viaducts where the train is going to pass. Okay, so these are like two different structures, separated structures. So the question is when the train is going to pass, whether the response is same or not. It should be same. Train is so fast. Yeah, of course there is an interaction. There is an interaction. So there are some like bearing system and the damping systems which has been kept between the two viaducts. Of course it is there. The general answer is the response should be same. But the problem was it was like under 40 years of service, the structure has deteriorated something like in a very bad manner, where the viaduct 7 is performing really bad comparing to viaduct 6. So these are all some of the, so now the question comes how to increase the speed from 1 to the 210 to 270. So this was some of the challenging problems which they had, and they tried to go for retrofitting. So see why I am showing this, because why bridge health monitoring is important, or the infrastructure which is used for transportation system is quite very much important, at least in Indian cases. Like we should be more like giving importance to this. I think in India is the only country where during construction bridge will fall. I mean, like we are getting at least one or two newses every month continuously. Okay, so which need to be like, safety is very important. Okay, so of course the structure design and the implementation is very important. Okay, so these are some of the famous yeah. Yes. No, not another speed. They want to increase. Yes. No, whether the if the speed is higher, the load will be higher. So they want to like check whether they could able to increase the load, because the trail tracks, the platforms, infrastructure need to be checked. You cannot for example, even in India, you cannot drastically change a speed from certain kilometer per hour to the another, because you need to check whether the track system and all other railway infrastructure is suitable for that particular speed. So yeah, there will be like more dynamic force that is going to act on the train. For example, like train system itself is something like having like a lot of complex and dynamics. So you have a train car body, then you have suspension systems, then wheel. Okay, so the train car and the suspensions, or I should not call that a suspension, I should call it as a bogie. Okay, so that is connected using primary suspension, where the bogie and the wheel is connected using the secondary suspension. So there are like too many components where the force transfer will be there, and at the end the track should be like safe to take that load. Okay, so if that is not there, and already it has been like many years, so the track would have been like deteriorated because of a lot of factors, like there will be cracks, squats, like many other factors, so which is going to lead to a derailment. Okay. Yes. No, for example, there is something called as this train, yeah, there is something called as wheel track bridge interaction. So that will affect like when you increase the speed. So that is a big concern. That's the reason in most part of India, at least today, they are not trying to go like beyond certain value of speed because of the old structures. So that's the major issue. If you also could able to read the recent articles for this Vande Bharat, so they are trying to have, I think that is having almost the maximum speed in India right now. Of course, they are planning for the bullet train in Ahmedabad, but even for that, they could not able to have a many plans because of the railway infrastructure. So they want to have the particular tracks where that speed limit can be like attempt. Okay, so that is possible. Otherwise, they won't recommend to have that Vande Bharat, because it's very simple to introduce Vande Bharat at every tracks, but like they don't do it because of the existing rail conditions. So that's the major issue that we have. Okay, so this is like a very big problem where the whole dynamics is going to change when you change the things. Yeah. So some of the case studies. So why this monitoring or inspection is important? So way back, maybe like in 1967, like there was some bridges which was not even considered about corrosion effect. Okay, so there was some lot of failures. Okay, so I'm just trying to show some failures. Yeah, this was like Minnesota in 2007. Okay, so there was a failure. So what you can observe from this figure, this is quite, so there are like two parallel, almost similar structures. One is standing good, but another one is like collapsed. Why? What is the reason? Almost they would have used the same type of designs, I guess. There won't be much soil change. Okay, so the foundation, everything will be same, but it has got like settlement, age. It is same. Yeah, the inflow, outflow, because the water is flowing in this manner, the whole load is something happening. First, it is taking by the piers. Okay, so there was settlement and the load was happening and the failure happens. So these are some of the strange problem or accidents that has happened, which has opened an eye for maintenance of the structure. Okay. Yeah, this one is a quite important case study that as an health monitoring thing we do it. Okay, which happens in Oklahoma I-40 bridge. Okay, so it got collapsed in 2002. So this was because of the collision of the freight. Okay, so because of this collision to the pier, okay, so the whole deck, it just came down. Okay, the bridge deck just came down. Okay, so the freight barrages being transported on the Arkansas River collided with the pier supporting the Interstate 40 road bridge crossing the river. So I think this is like quite important problem that we need to look into. Okay, so of course, like health monitoring by now, like you can write, so there are like various definitions. So basically, like I feel like health monitoring is something like a process for in-service health assessment. What do you mean by in-service? Something where the structure is in use. Okay, so through an automated monitoring system where this automated comes into play, where this advanced technologies we can add into. Okay, of course there should be always a cost effective strategy, because I am not able to spend too much money for just for monitoring purpose. No one is interested to monitor unless otherwise you have a problem. So how many of you visited doctor last time? Unless otherwise you have you don't go to a doctor unless you have a problem, right? Same thing, almost same. We are like, we could able to correlate SHM with the medical field. Okay, so doctor will monitor patient's health, we are going to monitor the structure. Okay, so it can be any. Okay, so they are going to use some medical equipment, we are going to use the sensors. I mean, even they are going to use sensors in a way. Okay, so they are going to give prescribed corrective medicines if required. Suppose like we are also going to have some measures, okay, to how to retrofit or correct that particular situation and come out of that thing. Okay, so that's what like we are going to do. So this is something like a very simple figure which is like self-explanatory, where we have like 5 sensing system which can be called as sensors, which is connected through nervous system, which is something like same as interpretation, where the information is passing from one part to the another, where the brain is processing. Similarly, we have one like database system where everything will be like integrated. Okay, so it's self-explanatory. Yeah, so only like we are concerned during the emergency situation, otherwise we are like not bothered about it. Okay, so there are like various factors. Okay, so wind, earthquake, some accidents, okay, some blast. So always the monitoring, okay, is always a good asset. Okay, so if you collect the data and you try to get some output of it, so it is like really good. Okay, you could able to at least stop the accident. Okay, so it will be really good. Okay, so that's what it says here. Yeah, there are like certain levels. Okay, so first one is the detection, then comes the localization. So identification is something called as localization. Okay, from the bottom to top. So then you have classification, type of damages. You have crack, corrosion, spalling of concrete, okay, rebar exposure, all those things. Then you're trying to assess it, whether it is how much the damage is. Okay, then you try to prognosis. Prognosis is something like you're trying to predict what will be the remaining lifetime. Okay, so first you have the determination of damage existence, then you are trying to understand the damage location, understand the geometry of it. Okay, then you are trying to quantify it, finally you are going to predict the remaining life. Okay, so this is the basic approach we follow for any problem that we try to take up. So this is something like a analysis that we do. Okay, so we just start from this red dot, okay, red circle. So first one is sensor selection and placement. So there was a big study that was happening in last few decades. What type of sensors you are going to use? What will be the optimal placement of your sensors? You have a bridge, okay, so you cannot place sensors everywhere or anywhere that you want. Okay, so there should be some constraint. So this is something like a basic dynamics. Okay, suppose let us try to imagine like I have a beam. Okay, let us consider a simply supported beam. Okay, so if I want to take the first mode, so where you will recommend me to place the sensor? So okay, first of all, let me know what is the first mode. Let us assume that I am going to like give some load here. What will be the first mode? So this is something like a simple first mode, right? So what will be the second mode? So there will be 1 0 crossing. Okay, so this will be something like mode 2. So what is mode 3? Okay, so now let us say this is like first mode and this is second mode. So now let me just draw again. So tell me where I should place the sensor to get that first mode. Any idea? In midspan? Sure? Okay, I am going to place a sensor in the midspan. This is sensor. So you are going to get the first mode. So if I want to get the mode 2, will I get? Yeah, so you cannot get mode 2 when you place a sensor at L/2 distance. You understand? So you should have some other placement location. Of course, if you have 2 sensors, that is different story. Okay, suppose if you have only 1 sensor, of course you can get odd modes. Okay, you can able to get, if it is at L/2, you can get odd number of modes for first, third, fifth. I mean, beyond this, we are not interested in civil engineering. So you suppose if I'm going to keep in L by, what happens? L by 4. What I will get? Suppose if I'm going to keep my sensor at L by 4. Exactly. So you're going to get somewhere like overlap. So of course you're going to get second, but there will be like overlap. Suppose if I'm going to change this to L by 3, what I will get? So you will get 1 and 2, correct? 1, 2. So now it is in the hands of engineers, okay, if you have like minimum number of sensors, always good to use minimum number of sensors and have an optimal sensor placement, okay. So I will choose L by 3 rather than L by 2 because I am more interested in first 1, 2 or maximum 3 modes, because that is going to give me the whole dynamics of the system, correct. So that's what the first point is, like what type of sensor am I going to use it and where am I going to place it, okay, that's very important. Then data acquisition, okay, what type of data am I going to collect, okay. So then data transmission. So nowadays we have like wireless sensors, okay. So wireless, I hope you would have come across wireless sensors, okay. So there are like different like variations in sensors, okay. So there are like some very costly sensors and there are like very cheap sensors which you buy it less than 100 rupees in Amazon, okay. So now you should have a very good data transmission system so that you are not going to lose any data that you are going to collect. That is very important, okay. Then data processing and control, okay. So how good you are going to process the data and how good you are going to manage it, okay. Those are like very important things. Then you have the health evaluation. Finally you are going to take the decision, okay, where it is going to be like inspection and maintenance process after like certain time, okay, time interval. So this is something like a detailed analysis we try to do in most of the projects. Only thing, sensor is going to vary, your processing technique is going to vary, okay, and like your duration is going to vary, depends, okay. There are like two types. One is like long term monitoring, something will be like short term monitoring, okay. So the strategy will be same, okay, fine. So now I think almost like we understood like what the SSM system is going to look like, okay. So when it comes to sensors, okay, so you have like two types. One is contact type sensors, another one is non-contact type sensors. So can you give me some examples of contact type sensors? Strain gauge. LVDT is contact or non-contact? Contact, okay. Anything else? Accelerometers. Yes. So whatever you are going to mount onto your structure or embed into your structure, it is contact. So some examples for non-contact. Yes. So camera, which is like a very like widely used nowadays, okay. So camera is one basic non-contact. Anything else? Yeah, so laser Doppler vibrometer. Anything else? Sorry? Sorry? Electromagnetic, okay. So IR, MR, fine. So these are all some of the non-contact based sensing system. Of course, the whole course in this week we are trying to rely upon the non-contact based, if you could able to think, yes. So we are just relying upon the video or the images that we have collected from the structures, okay. Fine. So anyway, like this is again the same thing, like how we could able to interpret the procedures, okay. So if it is like passive diagnosis, you have like strain gauges, okay, so which is going to collect the data. If it is going to be active, then you are going to use some smart sensors where it is going to have the real time monitoring. So for example, you can have some IoT based systems which is going to collect it, transfer the data to a cloud, and you would able to see real time what is happening in my site, okay. So those are like some of the advancement that is happening in past 5 years or like let us say 10 years max. So again, like as we discussed, there are like two types of monitoring. One is global, another one is local. So global is something like where you try to understand the scenario of your whole system, but when it comes to local, it is something like suppose if my bridge girder is corroded, so then I have to have a local monitoring, why it is corroded, how it is happening, all those things, okay. So and there are like different physical parameters, different sensors that I can use it to understand. that particular local system, because if the infrastructure is too large, okay, so it is not obvious to concentrate on whole structure, okay, which is like running for more than kilometers. It is always good to have a local monitoring, understand what is the reason for it, try to rectify it and come out of it, okay. So that's the basic things that we try to do, okay. Of course, global monitoring like simple dynamics, mode shape thing, that will help you to understand the system, but if you want to really understand why that is happening, local monitoring is very, very important, okay. So that is very important step, okay, to do it. Of course, components you understand, okay. So this is like very simple figure, so where you try to understand how the online health monitoring can be done, okay. So nowadays this is like quite simple, where you use wireless sensors. If you have a big system, structural system, you have like multiple sensors, so you try to communicate between the sensors. That is something called as multi-hop technique. You try to send the data from one point to the another. If you imagine this is like 1 kilometer, so you will have multiple sensors, but you will be sitting here, okay, which is something called as the sync node, okay. Sync node is something where you are going to collect all your data and process it, or you try to collect it, okay, do the processing point. So now, so from here it is easy to send to the sync node. Of course, you can send directly to sync node, or you can have a multi-hop. It will come first to here, then second to this system, then it comes to the sync node. Imagine you have a huge structure, there are too many sensors, okay. This sync node, there are like many other techniques. This multi-hop is something like very famous technique, where you try to collect the data without any loss of information, okay. That is very important, okay. So once you do it, you try to do the data interpretation and diagnosis, okay. That's the thing. So this is something like sensor and sensing technologies, okay, so which is used, okay. So one point which I would like to mention is that last one. There is no sensor in this world that can measure the damage. Please understand this, okay. So sensor is something, it is going to measure only the response of the system because of some action, okay, some stimulus, okay. It is something like the response that is getting collected, that's it. Only by interpreting those response you could able to say whether it is damaged, undamaged, healthy, unhealthy, all those things, okay. It's not that I'm going to have a sensor which is going to give you the damage. No, it is going to give you a response from there, where you could able to interpret and understand whether it is damaged, whether it is healthy, unhealthy, all those things, okay. So this data integration, like data interrogation procedures is something like very important, where that strategy is going to tell you whether the system is effective, cheap, like cost effective or not, okay. So if it is like too much procedure you have, then it will be like cost, like it will raise the cost, okay. So it should be like more careful in understanding to develop some effective solutions, okay. So of course, so are these systems damaged? Yes, right. So I think all are damaged, right. So this is something like relatable to our civil engineering, okay. I just took these pictures from various other thing, aerospace, marine. So this is because of some earthquake. So it has become like, so where earthquake will like try to like shatter the holes, like multi-story building, right, okay. So now what is the definition of damage? So there is, I think like I always ask this question, what is the difference between a damage and a failure? Both are similar, right, but it's not similar. Just think and respond. What is the one at a time? Good point. So which is ultimate? Failure. Very good. So that you understand, right? So damage, so it can be defined as something like there is a change in the material or the geometry properties of a structural or a mechanical system, including changes to the boundary conditions, system connectivity, that adversely affect the current or the future performance of that system, okay. This is something like a basic definition for a damage, okay. So there are like different types of damages, okay, so which I would able to give you with quick examples. If there is a crack in my system, so what type of damage is it? There's something called as the stiffness changes. Okay, so why I am showing this, because it will be easy for you to model, because generally as a researchers we try to model something, right, before we do some experiment. So if you want to simulate something, you can do these changes. Okay, so it will try to help us for that. Okay, so if there is some scour on bridge pier, okay, so what do you mean by scour? Any idea? So yeah, you're right. So suppose like if this is my bridge pier, okay, where my water level is something here, so this part is going to get eroded. Okay, so what happens is that, like, if you imagine that there is a disconnection with the land and the bridge pier, what will happen? So there will be some deformation, right? It will sink. Okay, so this is something called as bridge scouring, okay, which is a major issue, at least in the coastal zones. Okay, so this is something called as the boundary condition problem. Okay, so completely you are detached from the system. Okay, so then you have loss of tire balancing weight. So this is something like a mass change. Okay, we are not much concerned about this mass change in civil. Okay, we are more concerned about the stiffness change. If you have read many papers, no one will talk more about the mass change problem. They will always focus on the stiffness change in health monitoring, particularly to the civil domain. Loosening of bolt. No, mass change, if you see, like mostly in civil engineering problem, so for the dynamics part, we care more about the stiffness part. So mass is not going to play a major role in civil engineering thing. So this is something like loss of like tire balancing weight is like different example for the mechanical problem. So where this mass change is going to come for, but for civil engineering, like we never worry about much about the mass. Okay, so loosening of bolted joint, which is like a very big issue in the towers, transmission line towers, huge structures which will be standing, right, continuous things. So where the connectivity change will happen. So like because of this wind load, if there is some bolt missing or if there is some loose connection, that particular member will fall, or it will help, it will like try to like make the whole system to fall. Okay, so which is like a big issue. Okay, so I hope like we understood something on this health monitoring, like basics. Okay, so one of the primary detection problem is that visual inspection. Okay, so that is the primary, I mean we try to believe, right, that is something like a local non-destructive evaluation process that we try to carry out whatever maybe the system is. Okay, so even if it is like 40 years old building, first step is to have a visual inspection, what is happening, whether the connection is good, bad, how the material is deteriorating. Okay, you try to do the visual inspection. So these are like 4 different pictures which is trying to address 4 different domains of engineering. Okay, aerospace, bridge, of course, like we try to see in past, like before 2000 it was too tedious to do the monitoring process, but recently in this 5 years this drone based system is helping us to do the like process in a very easy manner. You just stand anywhere in the bridge and operate the drone instead of going to the site, stopping the traffic. You just imagine how difficult it would have been to do the visual inspection. Okay, so of course, like this is the wind turbine. So I hope you can imagine the height of the wind turbine. I think they have to climb. So nowadays there is a drone which can like the robotic systems. Okay, so which can climb over this, park at some platforms, then it could able to fly, come back. Okay, so there are a lot of advancement that is happening every day. This is for the marine structures. So no need to have a like a person to go and do the testing. So we can send the robots. Okay, similarly I can give various examples, pipelines. Okay, so there are a lot of things which has been like replaced with our advanced techniques. Okay, yeah, again, so this is the traditional inspection that we followed in the past, which is quite unsafe, laborious job, but where you need a skilled labor to do this. Okay, so but nowadays, like even inaccessible points can be accessed using some of the different types of drones, robots, so that like we could able to do the inspection in a very easy manner. Okay, so I hope like you understand these points. Yeah, so this is like as a person who is working in health monitoring, it is always good to know these things. Okay, in 1992, so I-40 bridge test was conducted. This was something like a first project which has been focusing on health monitoring. Okay, you should know this. because this was taught to me when I was a PhD student at University of Tokyo. My professor started his lecture with this slide. Okay, so I hope you are aware of this national laboratory, Los Alamos National Laboratory. Sorry, which one? Ah, yes, yes, that was Los Alamos. Yes, you're right. So Charles Farrar was a professor behind all these things. So even today, this Los Alamos National Laboratory is one of the pioneering research laboratory in the world. Okay, irrespective of a lot of academics like MIT, Illinois, Caltech, a lot of people are working on it, but this is one of the respected lab. Okay, so they have conducted, which was like, just imagine like how the setup has been made. You can see there is a person standing here. I believe you could able to observe this. So there is no crane system in those time. Okay, in 90s. So they tried to have a like a scaffoldings, like a truss, like steel members, and where someone is climbing using the ladder and is trying to do some accelerometer things. Okay. So yeah, these are all some of the sensors that has been used in different projects for the inspection. Okay, so this first one is the servo type biaxial accelerometers. So servo type is something like where the sensors are like very good. It could able to have the vibration capturing of that structure in a very easy manner. It has a lot of high sampling rate. It is quite costly. Maybe in Indian money it will be around 3 lakhs. One sensor I am talking about. So this is the installment of the sensors in the Shingma bridge. So you know where is Shingma bridge is located? Hong Kong, China. Okay, so I will show that case study. Okay, it's a very good case study. So because it is one of the first among the bridges where almost like more than 150 sensors have been installed and they are doing this real-time monitoring. Of course, nowadays many people are doing it, but they even after opening to the traffic, they did that. They are trying to carry out that monitoring. The next figure is something like Canton Tower. They try to install the accelerometers to understand the vibration. Okay, so the model of that sensor is like Tokyo Shokokin model. So which is like very high-end model. I mean during those days. Okay, nowadays we have a lot of things. Yeah, these are all some of the very well-known strain gauges. I hope you would have used strain gauges, right? So where you try to connect to some system, but this is something quite different. Nowadays we have, it's not moving. I think I got disconnected. I will try to join again. Yeah. So I hope it is visible. Yeah. So this is like different type of strain gauge. So what is the specialty of the strain gauge? Can you observe and tell? Have you ever seen this? Exactly. So you could able to see that is connected to some wireless antenna system. So where you could able to use this. Previously, like you can never take strain gauge and like connect like this. You need to have like a lot of wires coming out with the DAC system, which is like very hectic process. Sometimes it will not work. Okay. So nowadays there are a lot of advancement. That's what I would like to show. Okay. So this is like very good strain gauge, which is like So the strain gauge is going to give you the strain variation only at that particular location. That's a disadvantage. To avoid that, if you want to have a continuous profile of strain, what you will use? Any idea? Have you ever heard about this fiber FBG, fiber Bragg grating sensors? So you try to like paste the wire throughout this board, you could able to get the strain variation along the length. Okay, so that's the advantage of it. So that became quite famous. I mean, in India it is not famous, but it became quite famous in UK because Professor Kenichi Soga from University of Cambridge, he used the fiber grid strain gauge throughout the tunnel, because in London, like, there are a lot of underground tunnels. Okay, there are a lot of connectivity. So you used throughout the tunnel to understand the strain profile, which no one has done. So it was like a big project they had. So where that sensor became so much popular. I'm just saying around 2010. Okay, so but nowadays it's not quite popular. So this is something like crack detection sensor. So wherever there is a opening of crack, you will have a sensor where it is going to like activate. Okay, so and it is going to tell us whether it is I mean, it is like unsafe. You need to like look into that part. Okay, so there are a lot of, it's something like a bandage you try to put. Okay, so yeah, yeah, no, I think this you can reuse, this you cannot reuse. Yes, no. So these are accelerometers. I hope you are aware of accelerometers. Yeah, this was the fiber optic sensors which I was mentioning. So throughout the system you could able to stick wherever you want, so that you would able to understand the strain profile. Okay, so that's the advantage of it. Only problem with this is like it is like too much wire is involved. You need to go stick it, all those things. Okay. Yeah, this is like today's thing, like where everyone use this, right? You try to use the IoT based smart sensors. You try to like mount anywhere that you want. It is going to do the job for us. Okay. So there are like various, there are many things. Okay, I'm just trying to put some like famous things which we have used. Okay, iMode 2 we have used, high sensitivity accelerometer we have used. That's like a DAC board. Okay, this is for the strain, and that is for the wind pressure. There are like many things like we are using it. So the basic process is something like you have a data acquisition. The second point is like cleansing. So what is mean by cleansing of data? It's like self-explanatory. Huh? Yeah, removing the noise. It's something like filtering. Okay, the unwanted things. So then you try to use some system identification methods to extract the information. Okay, so it can be any. Okay, so any method you can use. So once you do the feature extraction, at the end we will try to understand the model parameters. Then you have the diagnosis and prognosis. Okay, this is the basic things that we try to do. Okay. Oh yeah, I was trying to explain about this multi-hop techniques, right? This is what this digital sensor network looks like. Okay, you have one host, you have a lot of routers in between, and that one router is going to control the wireless thing. It's almost like Wi-Fi that we are going to use, right? That the same technique is used for the wireless sensors. You have one router point, and you try to have different sensors. From there, you try to collect the data. Okay, so global network system and local network system, so you can have a control over it. Okay, so yeah, and one more thing is like time synchronization for wireless system. So this is like very important thing, because when you use too many sensors, not all the sensors are going to be, I mean, it's not going to follow the same clock, right? It has its own things. Okay, so whichever sensor you believe that is going to work, it will not work during the site. Okay, so I have like too many experience out of it. So which, I mean, like one day I will tell the story. I have that pictures where we repeated the whole experiment. Okay, so because like that one sensor was not working. So this was like, yeah, if you do these things, like you will have that pain. Okay, so the very important thing is like time synchronization, where you have different clock for the sensor system, but while you are going to analyze the data, it should have a same clock. Otherwise, you will not able to compare and have a discussion out of it. You are not able to infer anything from the data. So you should have a time synchronization point for the data processing. Okay, so that is like very important point that you have to do when you are dealing with many number of sensors. Okay. So then comes the very important point, that is like vibration based methods. I think we are discussing more about this, so no need to spend time on this. Okay, so let me just skip. These are some of the types of sensors that can be used in field. Okay, along with this we are going to use the drone based system to understand using some, I mean, like till date the government is not willing to use like drone based system and understand this deep vision. People sitting there, like, they are not so much comfortable in understanding those things. That is fine, but they want to have the traditional method of contact sensors, get the acceleration data, find the frequency, plot some like mode shape, compare with the abacus or ANSYS analysis, and they want that dynamic analysis. Okay, so these are some of the typical sensor types that we can use it. Okay, I hope you would have come across all these things: triaxial servo type, strain gauge, load cell, okay, GPS system, biaxial tilt meter. Okay, so yeah, these are some of the various monitoring quantities. If it is a cable, what type of sensors I should use? If it is like like different types of systems I could able to install if it is like a cable stayed bridge. Okay, so some of the things. This is for the highway traffic loads. If you want to monitor the railway traffic loads, what type of monitoring system that I can use? Okay, there are many things. So highway traffic composition, highway traffic loading spectrum, daily highway traffic characteristic. If you want to understand what is the highway traffic, okay, to quantifying that. So for the railway thing, same. So we can use the dynamic or the static strain gauges. You can go with the high definition video cameras. Okay, so these are some of the basic things that we generally use. Okay, practical usage points. Yeah, so this is the things. Okay, so I hope you try to understand this schematic picture. Okay, so where you try to install some conventional accelerometers which is connected through the DAC. Of course, nowadays this wires or cables have been replaced with wireless sensors, and along with it you have some standard video cameras to do the measurement. From there you try to extract the data points. Okay, so this is the Sigma bridge. Okay, so which I was mentioning. Okay, which is like world's 14th longest like suspension bridge. I hope you understand the difference between suspension bridge and cable stayed bridge. Yes, can someone quickly explain that? Don't think both are same. What is the difference between suspension bridge and cable stayed bridge? No one? Okay, you can guess the same explanation from this figure. Okay, so then what is cable stayed? Correct. So you guys get it, what he is saying? Yes, sorry, wooden. Oh, golden bridge. Golden bridge is suspension bridge. Rabindra. So in the middle there is a pylon, or? Uh-huh. Okay, so then I am not aware of that. That is cable stayed. Okay, where is it? Achha, West Bengal. Okay. Sorry, I am not. Yes, yes. So if that is the case, then it will be like cable stayed. So the whole force is taken by the tendons. That's the reason this is like suspended. Okay, so suppose like you have some like thing. If you want to tie something in this corner of this in a thread, and if you hold the tip of the thread, the whole object is going to suspend from there. Okay, so where that thread is taking that whole load. That's the basic definition for it. If there is different system of transfer of load mechanism, then that will be like categorized as the cable stayed. Okay, so if you could able to look careful, but like nowadays the because of aesthetics they are like complicating the things, but if you would able to carefully look into the structure, you would able to identify that. Okay, so there was like bridge health monitoring system where they call this as wind and structure health monitoring, okay, which was installed and operated on the Shingma bridge since its opening, that is 1997. Okay, so it's almost like 20 years, right? So they tried to install 283 sensors, okay, which is like too much costlier. Okay, you just imagine in 1997, because they want to do the continuous long term study. Okay, so they had like 8 types of sensors which I have like mentioned here. So anemometers is used for what? Wind velocity, okay, so to measure that. Then servo type accelerometers, temperature, strain gauge, GPS, displacement transducers, like level sensing stations and weighing systems. Okay, so these are like basic 8 things they have used. Let me just show that figure. Yeah, so you could able to see how the sensing placement is done here. So among the 283, the maximum sensor was temperature sensor and the strain gauge. Okay, so you could able to imagine how the analysis would have been taken place, how the data processing they would have done, how much data they would have collected. Okay, so it's a big project. Okay, and there are like too many case studies that has been coming out from this. Okay, so which is a good case study to study. Okay, yeah, I think that's the symbol, GPS. Yeah, yes, there are like 14 GPS systems. I'm not aware why they are kept 14. Yeah, that's what I'm saying. So that optimal sensing placement is very important. It's not that since they're using 283 randomly they're not going to put. For every placement there is a like explanation behind it. Why am I placing here? Okay, so this is like very good case study. Okay, so I'm just trying to introduce. If you're interested, you can go through these things. Okay, yeah, this is the system that they proposed, which is a very basic system, which now it looks very simple, but imagine 1997. So they have done a very good work. Okay, so they are trying to do the same thing. First, module 1 is the sensor system, data acquisition, processing, okay, evaluation, managing those things, and again do some analytical study, create some like fundamental models and understand. Okay, so this was like proposed like long back. Okay, so I'm just showing it how they have used it. Yeah, these are some of the popular health monitoring benchmarks. If someone is really interested, they could able to go through this. So every country has its own like schemes, like where a lot of projects are funded. Okay, so in US, like majority of research projects are funded by NSF, National Science Foundation. I think we recently have this DST changed to Anushandan like Research Foundation, which is having some correlation with this NSF. Okay, that's the idea they had. Okay, Federal Highway Administration, like NASA. I hope you all know that. Then California Transportation Department, PEER, Pacific Earthquake Research, Engineering Research. These are like very famous sponsoring agencies where they do a lot of case studies. Okay, and it is like a benchmark problem for us. Okay, similarly in Europe there are like a couple of things. In UK, Australia, there are like many things. Okay, I think in India they are trying to develop some of the codal provision as per the request from the IRC, Indian Road Congress. Soon I think it will be released. Okay, so before we go into this strategy of health evaluation and maintenance for bridges, so we'll try to enter into this computer vision part now. So until now, if you have any questions, we can take it up. Because till now I didn't talk anything on advanced topic. Whatever is there existing, very simple practical cases only we discussed. Okay, I'm just trying to introduce why health monitoring is more important for bridge infrastructures, particularly for maintenance and the inspection purpose. Okay, so from here onwards we will try to go into the effective strategies where this computer vision is going to play a major role. If you have any questions, You can ask. If not, we can continue. Any questions? No? Fine. So we'll try to continue. So for example, like, so effective SHM strategies, again, like there are like a lot of theories, but the aim is what? We need to have a cost effective system where we are going to do the automated health monitoring. That's it. So these are the two key points which we discussed for the definition of health monitoring. That is going to play a major, that should be in our mind. So how we are going to do it? So there comes the strategies. Okay. Yeah. So again, like these are all some of the like strategies which have been like followed by many countries. Okay. So for the safer bridges and the longer lifetimes, some of the things that they are trying to propose. The first one is the infrastructure assessment. Okay, so selection of monitoring targets according to the structural peculiarities in cooperation with partners. Okay, so there will be like different stakeholders. So we need to have a like cooperation with the stakeholders to understand how the maintenance can be made. Okay, some of the policies that has to be released, because in India at least we don't have a policy. So unless there is a big problem, we are not even concerned about that structure. In India, at least in East Coast, there are like many bridges which is more than 50 years. Okay, so many railway bridges. So now when there is a problem of this deflection, then they open their eyes. Okay, but there should be like continuous monitoring and inspection to understand how my structure is behaving. Okay. The second one is planning and design. Okay, so how you are going to like plan. Okay, so how you are going to customize your sensors and do the monitoring system. The third one is the installation. Okay, so installation here means that not that you just go keep your sensors, but also like have that monitoring of those data, how you are going to send the data, how you are going to analyze all those things. So data and equipment management. So how we could able to do. At the end, something called as the continuous monitoring and maintenance. Okay, so which is like real time and also for the long term monitoring. Okay, which is like very important. Okay, it's not that like I just go monitor and come back. It's something like where I have to install and monitor for next 3 months, 6 months. So this monitoring will help you to understand how your structures are behaving for various loading conditions. Okay, so which is like very important point that we have to take care. Some of the frameworks which has been like most commonly utilized nowadays, you have a numerical simulation at one side, you have data that has been collected, you try to compare, do some analysis, do some diagnosis and prognosis, and you're trying to predict the life. So this is something like a very simple framework that we could able to propose for any system that we have. Okay. Yeah. So some of the advanced computer vision techniques that we have carried out. So one is the like phase-based motion magnification method. So I hope you understand from the term motion magnification, right? So someone have heard about this technique earlier. Suppose like you have the vibration which is like very small. So now let us assume this fan. So is this fan vibrating? Yes or no? This one? No? So obviously this is vibrating, which is not visible to us. It is having some subtle motion. Any system that is there which is prone to the normal environmental ambient condition, it is vibrating. So no, this is like yeah, of course this is, no, yeah, that is fine. Of course it is vibrating more comparing to this, but if you want to have a system which is like prone to the ambient condition, obviously that system is vibrating, that is for sure. So now how am I going to extract the vibration from here? How am I going to extract the measurement or response from here? If I'm going to have a camera and like capture this for let us say 20 seconds, so can I extract the response of vibration from this? Yes, we can do it. That's what I'm going to show. Okay, so that's the power of this motion magnification method. So since it is vibrating, unless otherwise your system is inside a vacuum, we can have a debate whether it is vibrating or not. But if it is in an ambient condition, I can assure you that it is vibrating, and which is not visible to us. If I'm going to do a capturing of this camera and run the computer vision technique which I have proposed here, we can extract the response from here. Okay, that's the point here. Okay, so which is quite interesting. Okay, but this was done like maybe in 2018-19 I did, but Now it is like quite old. Okay, we have done a lot of more works after this, but it's since it was like in 2015, okay, the first research article is coming out from MIT, okay, group, okay. So though this technique was used in computer science field as an application for the civil engineering, okay, so it was coming out in 2015 from the MIT group, okay, Professor Oral. So the postdoctoral fellow's name was Justin Chen. You can check now. I think he's in some big lab. So that was the motivation why we could not be able to use for the different practical cases. Okay, that's the reason we took up this project. Okay, so let me just go through the flow chart. Okay, the first one is the phase-based motion magnification method. Let us try to break down this. This phase-based. Okay, so what do you mean by phase? You have a signal. So when you try to talk about phase, any idea? I mean, let us come back to this small dynamics part. Okay, so just go into the dynamics mode. So where you discuss about a phase of a signal, frequency. Okay, that's a good point. Think in that manner. Yeah, yes, good, that's good, that's a good point. So here, like what I mentioned about this phase base is something coming from this frequency part. Okay, so when you have a time domain signal, okay, and you try to convert that into a frequency domain, so let us assume this Fourier transform, which is like well known to everyone. I assume that. Okay, so you have two parameters that you are going to get. One is amplitude and another one is phase of a signal. Okay, so now once I get these two parts, I'm just going to play with this phase of this signal and I'm going to magnify that part to understand how that system is vibrating. That's what we're going to do. That's the simple layman explanation I could able to give now. Okay, so now first step, I'm going to measure the video. Then I'm going to implement the two-dimensional Fourier transform and filtering techniques. So why am I going to give two-dimensional? Any idea? Exactly. So video is in 2D. So I have a video which is like a normal thing, and for that video it is going to have an FPS, frames per second. I could able to convert that video into frames, number of images. Then one single image you take, that is an XY coordinate. I'm just going to implement the Fourier transform for it. Okay, and yes, separate, yes, each image. Now then we are going to apply some filtering part. I will come back to this filtering. It's like a normal band pass filter. So I hope you understand what is a band pass filter is. Yes, so you have a low frequency cutoff and high frequency cutoff. Okay, so then you have the multi-scale image decomposition. So where here we are using some complex steerable pyramid. It's like one method we are using. Then you have phase magnification. For each frame I'm going to magnify that frame. Then what am I going to do? I'm just talking everything about one single frame, which I'm going to repeat for number of frames, which is going to be finally reconstructed into a video. Okay, so once I do the phase magnification for one frame, next I'm just going to the Otsu method, which is like old Japanese method. So where they try to convert the RGB image into the grayscale. Okay, I hope you understand what is an RGB image. Okay, because whatever you take as a video now, it's in RGB. Okay, so red, green, blue. Okay, so now then comes the conversion into the grayscale. Once you have a grayscale, then you have a binary image. You can easily convert. So why am I converting into binary image? Because to deal a particular frame in 0 and 1. Okay, that's the binary. I could able to have an advantage of dealing that. That's the reason we do here. Then I try to fix some cutoff thing, threshold. Then from there will be some distorted mass. From there I'm going to select one point. That point is something like central of that irregular shape mass. From there I'm going to extract the time history response. Then once I get the time history response, then I'm going to implement a very simple like operational mode analysis. Here we have used random decrement method, whether to get the modal parameters, to extract the modal frequencies and damping ratio. That's the basic like 3 steps I could able to say, or 3 phases, okay, that we could able to do. Okay, so maybe like I will try to explain this with some examples, then you will understand more. Okay, so for conducting this we have done some experiments. So these are some of the types of sensors that I have used. Okay, so the first one is a sync node, which I could able to connect that USB with my laptop. Okay, then I have a wireless sensors. That wireless sensor is nothing but the very simple accelerometer, okay, which I'm going to mount on this shear building, okay, 2D of shear building, which is like an made up of aluminum, which is kept over the uniaxial shake table, which it is going to shake in only one direction. Okay. So now some of the parameters about the sensors. The sampling frequency is 100 hertz. So if my sampling frequency is 100 hertz, so up to what level I could able to measure the vibration? 50 hertz. Okay. So as per the Nyquist rule, sampling frequency by 2. Okay. That's the rule. Okay. So that's the reason, like, at least we should have 60 sampling frequency for a sensor for civil engineering. Okay. 60 or at least 30. Okay. So that, like, the civil engineering structures will be in the range of less than 10 hertz. Okay. Yeah, so this is the video cam that we used. It's like a very normal video cam which we use for marriage, right? It's like a normal Sony NX cam. Okay. So which we are using it. So anyway, like, let us go to the yeah, this is something like small math, same repetition what I have told here. Like, first you try to understand the I x plus del x comma t. It is something trying to mention the intensity of your certain pixel. Okay. So you have I is something like image intensity, x plus del is something like where you have that motion. Okay, where there is some extra thing that is happening. Okay, delta x comma t is something because of the spatio-temporal variation. Okay, that's what it is representing. Similar steps which it is just in theory. Okay, so you try to do two-dimensional fast Fourier transform, multi-scale and the localized filter, displacement extraction using Otsu method. Finally, you are going to do the extraction of the modal parameters. Okay, so this is the experimental setup. Okay, so very simple experiment. You have a frame where you have kept that wireless sensors. I hope you could able to see that small white box with an antenna. Yes, note 2, 3 and 4. Okay. So now I have a video camera here. Okay. So I'm just trying to give a small tap to the system so that I could able to get some like vibration measurement in my accelerometer. That's the aim. So then once it comes to the rest, I'm just going to collect the video of it and trying to compare the frequency that is obtained from the accelerometer with respect to the measurement that has been done using my camera and doing all those steps which I explained. Okay. So this is the data that is collected from the accelerometers. It is so good to see, right? Because it's like a shear building. It is going to like have a very good like mode shapes. Okay. So that's what we have obtained. Node 3 and node 4, you could able to see the just the difference in the amplitude for the acceleration, but it is having a very good match with the signal and you are getting the very good FFT of it, where it is the peak frequency is matching 1.855 hertz and the second one is 6.05. Please try to remember this value. So now I'm just trying to do the same procedure which we explained. I'm just showing you for one frame. This is like 570th frame. I think this is the last frame I had in my video. So I'm just trying to convert into grayscale, convert into binary image. Yeah, so this is the displacement response, okay, which has been extracted, okay, from the video measurement. So now the first one, okay, in this figure for the first mode, if you could able to see the first subplot, which is like so much random, okay. So I could not able to guess anything from that like difference of that movement of the system. Okay. So now I am just trying to apply some system identification technique. A random decrement method has been applied. Why? Because to get a free decay signal. Why I should need a free decay signal? What is the reason for getting a free decay signal in dynamics? Any idea? Just compare maybe this side. If you see the first two plots, you can appreciate the free decaying signal. Yes, I hope you understand what is free decaying, right? So you have a signal, okay. So if it is, so this is something like a normal signal. If my signal to have a decay like this, okay, this is something called as the free decay. So why I need a free decay? Any idea? Exactly. Yes, you're right. So free decay signal will help you to understand the modal parameters of a structure, any system. Okay, that's the reason we always try to get the free decay signal. Okay, so we try to disturb the system and we'll wait until it is coming to rest and we try to measure all the responses. Okay, that's so where you could able to get the difference in frequency values and also you could able to get the damping. Okay, so that's the reason we have used this. It's like a powerful technique. From there we could able to get these values 1.855 and 6.09. Almost it is having a very good match with the values that you obtain from the accelerometer. Okay. Fine. So this is for the cantilever beam, which is like a very simple experiment. So here I could not able to mount an accelerometer on to the scale. Why? Because that will, the additional mass is going to create a difference in my measurement. So we try to use the laser Doppler vibrometer, which is again a non-contact based system, which is a very robust system, but it's quite expensive, I guess. Okay, so we could not able to afford it, and of course we have our video cam. So nowadays you could able to replace this video cam using your smartphone. That I hope everyone have a smartphone here. Okay. So this is the displacement response, which is obtained using LDV. So even from LDV you could able to see it's already obtaining a free decay signal, because it's a cantilever. You try to disturb it, it will vibrate and it will come to a state. Okay, and you are getting a very neat peak, which is at 2.83 hertz. So now, yeah, this is the laser, just to understand the displacement part. Yes, yeah, here we measure the video exactly. Why I'm using this phase, I hope you can understand it. Out of plane motion I need, that's the reason. Yeah, good observation. So now here I'm just taking a random frame, 1/40th frame, and I'm just magnifying it, converting everything, and I'm just doing the process. I would able to show that in different frame rate. Okay, so this is the response that we collected from the video cam. Okay, so where you could able to have a very neat peak around 2.8 hertz, which is exactly matching with the results that we obtained from the laser Doppler. So this gives a lot of confidence in using a video cam for this. Okay, so this is something like, before we go into the proper site that has been allotted to us, we just randomly took it to the road and we are just doing it. Okay, so let me just play this. Okay, so can you ever see any vibration in this first bridge? Okay, I'm just standing in pedestrian and I was taking this video. So can you observe any vibration? Yes or no? So you cannot observe it, right? So now after implementing this technique, just tell me, can you observe or not? Can you observe some vibration? Okay, so the technique is working. Okay, so that gave us some confidence. So the problem statement what we had was to understand the dynamics of this light pole, which is like a secondary member of any bridge element. Okay, bridge structure, which generally is not considered for the bridge design part. But in Kobe earthquake, so the bridge design was too good and bridges were safe, but all these light poles were damaged. Because of this, traffic was stopped. So there is a company called Kajima Corporation, steel company, where they want to understand the dynamics of the light pole, which is a secondary element. So we just try to take a video of a light pole, because it's very tedious to go to each light pole, install a sensor, give a huge vibration in wooden thing, then it will vibrate, collect it, analyze. It's very tedious process. So, and there are like too many number of light poles. So the aim was to use this computation techniques, where you could able to collect as many light poles as possible using a videos, then try to run the program and collect the data. That's a very simple thing. Okay, that's what we're going to do. So this is the bridge site that we went to understand the things. So this is like Shin Nakagawa Bridge in Japan. Okay, so it's a very beautiful bridge in Nakagawa Prefecture. Okay, so this is the bridge like we are trying to monitor. So I'll try to show. So it looks too good, right? So we went early in the morning. Okay, so that's the reason it's so good. Yes, this suspension. No, but cable is taking the whole load, right? This suspension. Yes. Let me just go to the results. Some interesting results we have. So this is the lateral mode. Okay, girder. Okay, from the bottom I'm just having my camera and like trying to collect the data. Okay, so this is the original response that is collected. So ambient condition. So vibration is invisible. We are not able to see any vibrations. Okay, let me play this. After applying the motion magnification for almost 100 times, we magnified. So you could be able to observe the vibration, right? So I remember in this experiment we were waiting if some car will not pass or not, because it was early. So luckily we have a video where car is passing and we could able to have a very good vibration. Okay. Yeah, so this is the results that is obtained. Okay, so first girder lateral mode using the Dyna software simulation, which was like 0.44 hertz, but using this like technique what I just discussed, you could able to see the vibration from there. The first mode is almost around like 0.46 hertz, which is like having a very good match. Okay, similarly, like this is for the y direction. Okay, because what we understood was it is not having a clear cut lateral motion, it is having something like in both in x and y. So we thought like we'll collect both the vibration data and we try to analyze. Almost both the things are having a same results, 0.46. Okay. Yeah, so this is the vertical mode which I was explaining, where we were waiting that one car will pass. Okay, so this is the original response which I have already played. Okay, this side, and yeah, I hope you saw that car passing, right? Okay, so this is good for us, but still there is no vibration that I could able to see here. But let me just play this. You can observe the vertical motion. So you will have like too much disturbance. So when that car passage happens, okay. So this is something like exciting the vertical mode of that girder. Okay. I hope, should I need to play again? Is it fine? First one, okay. First one you will not observe any vibration. At least you can able to see that some one or two cars will pass. Yes. So okay, let me play this again. So you can observe the vibration, right? Vertical motion. Where? This one. That is maybe at the other side there might be some pole. Which lane you're talking about? This one at the bottom. That is different, right? That is something other side of the bridge. There is some other structure or some other thing. No. I'm just taking a video of at one particular point, and we are trying to like do the analysis as I explained. Then I'm trying to reconstruct that video and playing it again for you. So now like, okay, so now you have, first I'm taking a video, I'm trying to decompose into number of frames. I'm trying to now talk about one frame, first frame. Let us assume there are like 1000 frames. So whatever I'm going to do with the first frame, I'm trying to repeat it for all remaining 999 frames. So once I do that in the like simulation, then I try to reconstruct all the images put together into one single video. That's what I'm playing in the other side. So this is the original video that has been taken. This is something like video which has been processed using the proposed technique and reconstructed for the motion magnification, and it has been played. Okay. So this is just like same thing how we have done that. Okay. So the frame resolution was like good resolution we had, 1440 cross 1440 cross 753, where 753 is mentioning the number of frames. Okay. So this is the frame that we have taken. Yeah, so these are all the results. Though it looks so random, any dynamics person, if he sees, he will not understand, he will not appreciate the signal that we get. But when it is going to match with the frequency spectra, it is like quite good for us. Okay. Yeah, so this is like one bridge. I think like in our campus there was a bridge in Yokohama prefecture, so where there was a bridge crossing over the university and the residential part. Okay, so they try to, so we try to do the experiment here as well. So yeah, these are the numerical models that has been conducted in abacus. So I'm just showing this to understand the modes, how it is trying to vary. Okay. Yeah. So this is the original response. So I have marked that yellow line so that you could able to appreciate the vibration that is captured. Okay. So this is the original response. You could not able to observe any vibration or the motion. Okay. This is for the lateral. Okay. It has to lateral motion. So let me just go to the next slide and play it. Yeah. Let me just play this. See, you could able to easily extract the lateral motion. Okay. So how that bridge is vibrating. Okay. Yeah. Yeah. First mode. Yes. Right. Yes. Yeah. Damping also we can calculate if because if you have a free decay signal, it is very simple to calculate the damping. Yes. You can apply a very basic logarithmic decrement method and you can extract. Yes. Yeah. That's what we are doing. This is what we are doing is operational mode analysis. Yes. You're right. Yeah, exactly. So there in mode analysis there are like two types. One is called as experimental mode analysis. Another one is called as the operational mode analysis. So difference is in experimental mode analysis you try to go to the site and excite the structure. That means the input excitation, the source is known to us. Using that input, you are going to collect the output and you do the analysis and get the model, do the model analysis. In operational mode analysis, this input is unknown because we don't know what is that exciting factor. We are not aware of what force is going to excite my structure, and I'm only relying upon the output response that has been captured or collected using my any type of sensors. So that is something. So whatever we are doing or discussing, almost everything nowadays is operational mode analysis, because nowadays we are not going to a site for exciting. That's the reason we wait for some like wind, for light structures we wait for some wind thing, or for generally for bridges we always wait for some big truck to pass. Yeah. So because it will be automatically it will be exciting. So that's what we also did here. Yeah. I hope you could able to appreciate the uh, motion. Okay. So from here you could able to capture the responses. Okay. Yeah, this is for the lateral motion. Okay. So quite difficult to observe any. Yeah, you could able to see in the shadow that let me just play again. See, you could able to see in the shadow that like at the bottom some vehicles are passing. Let me play this. So this is the lateral motion. Okay. So because of that reflection we are having some disturbed things, but like we could able to get this. Yeah, I think you could able to understand that lateral vibration part. Okay. Yeah, I think this picture will give you a better thing. Yeah. Yeah, so this is for the lateral motion. I hope you can easily observe that lateral part. Okay. Yes, it is having that neat motion. Okay. So these are the data that has been collected. You just see how good the vibrations are, and we could able to exactly match with the response that we collected. Okay, from the model. Okay. Okay. So now before I go into the next step, so it looks like any questions like. Yeah. Which displacement? Yeah. Uh, I think for the laboratory experiment, of course, we compared with the laser Doppler vibrometer, the displacement part, but our focus was more on the frequency value, because like sometimes like we have a random inside, it's very difficult to have a exact match with the displacement. So we are like okay with the difference in amplitude, but we are more focused on the modal parameters rather than the displacement. So I'm more interested in the frequency domain rather than time domain. If I could able to match the frequency, then I felt that was like good success we had. But yeah, please. Yes, it was like quite very good match we had, because it's a controlled experiment. The two for the cantilever I was showing, right? We could able to get a very neat free decay signal. Yes, I think some. Yes. I mean, it's something like we had a tripod system, and there is something called as anti-shocking thing, which you just switch on in that video cam. That's it. I mean, rather than holding in hand, there will be human error. So it is always better to go with the tripod system. Make sure that the surface is not disturbed. That's it. Like, no need to. Uh, yeah, no. I think like whatever we did was something like we are always focused on the like on the structure which is like flying over. So we were happily standing on the pedestrian part on road, and I was just placing my tripod and like I'm just capturing the video. So if okay, I understood that if my base itself is vibrating, yeah, that is possible. Maybe if you're standing in one bridge and if you're capturing another bridge and if your bridge is vibrating, then better to have some sensor on tripod and try to capture that signal and minus that signal. That's it. That's a simple thing that we do. Because yeah, there was one experiment we did where we were standing on the bridge and we are doing some other experiment for this different structure nearby. So whenever the big vehicle passes, we could able to feel that thing. So what we did was we tried to install one sensor, small accelerometer to the tripod, just to understand wherever there is a difference in that accelerometer data. We try to look into that exact time step, what is happening to my data, which is really that is recorded. So that is one possible way, but better to avoid those locations. I suggest to keep somewhere where there is no disturbance, so that like you will have a good recording. It will not come now. Why it will come? If you are going to walk somewhere like no, it will not vibrate, right? Only the structure like which is like having, for example, this like different top structure will vibrate. If you are standing on ground, if some vehicle is passing, do you feel the vibration? No, right? Mm-hmm. Yeah. Yeah, that is true, but I think like you need to find a location where there won't be any disturbance. Generally, wherever we did experiment, we just chose the pedestrians, and like we just bifurcated those points that like so that like no one is going to disturb that location. We just had that tapes. That's it. It was quite straightforward. Yes. Yeah, we can filter it out. No, but he is saying that if there is some vehicle is passing, if there is some disturbance, how to avoid it. Uh, yeah, we should choose a place such that it is not there. Yeah, yeah. Ah, which one? Yeah. Okay, lateral and vertical. I'm just changing my camera position. That's it. Yes, yes. Yeah. Yes, you're right. Yeah, actually, like it's a good question. What happened was when I tried to so whenever there is a passage of vehicle, so my light pole is vibrating, which I could able to understand from my video. But the problem is it is not vibrating in X or Y. It is having a spiral mode. It is vibrating something like this, which I think I have a video, but I didn't put here. But we have like this. But only thing is like my camera is having XY thing, which I could able to extract in X direction, Y direction. From that one single video, I could able to like process both X and Y. So we didn't do any decoupling as such. Since we had that XY plane in my camera that I captured, we can easily extract that X direction, Y direction pixel, and we did that. But like as you said, like pole is having some this spiral mode, which we could not able to do anything. We could not able to avoid that which is happening on site. So with respect to that particular direction, you can extract the pixels and you can implement the technique. Yeah. Okay, so before we move ahead, maybe I will stop here. We will have a break and we'll come back. Is it fine, or we'll have a break?